So before I start for today, I wanted to talk about, oh, hang on, there we go. The final class project. There is a project proposal that will be due at the end of next week. So we are kind of just about rounding out all of the non-policy lectures about electric vehicles. Next week will kind of be the last week about that before we wrap things up and kind of dive into policies related to electric vehicles. And so it's kind of a good time to start thinking about what you are going to want to work on for your final project. It's basically just going to be a paper going into more detail about any topic that you guys find particularly interesting. There's more information about the guidelines available on Canvas. And you can work in groups of 2 or 3 people for the final project. And the proposal here, it's nothing too complicated. Just want to make sure that folks start thinking about their final topic and working on it before the sort of last week. And this will also give me an opportunity to provide feedback if any of the projects need it. Okay, any questions about this or concerns? Great. Okay, so the topic of today's lecture, near and dear to my heart, thinking about electricity grid. So I mentioned at the beginning of class, a lot of my motivation in this area is related to climate change. And so I really got into electric vehicles kind of through this topic. So we've talked about all these things related to buying and owning an electric vehicle, how you might travel with it, how you might charge with it. But now we're going to think about kind of what happens when you plug your car in, besides, right, charging the vehicle itself. Okay, there's all this stuff that happens upstream. And so we're going to do a little bit more in-depth dive into the electricity system that we have in the United States. Generally, we can break down the grid into kind of 3 major systems. You've got your generation, and that refers to essentially all of the power plants. This is where electricity itself is produced from some kind of input, either fuel or energy. And so thinking about the various types of power plants, which we'll go through today. Once that electricity is generated, it needs to make its way from that power generation all the way to the end users, right? Typically, it's going to be your homes or commercial buildings, industrial buildings, that sort of thing. And so it's not often, so I'll caveat this in a second, but it's not often, right, that power plants are located right next to your house. Right? Oftentimes, electricity needs to be transmitted sort of really long distances. There is a sort of new set of technologies, distributed energy resources. So you might think of things like rooftop solar, where you're starting to break away from the norm. But the vast majority of power is coming from these power plants that might be located, hundreds of miles away from where the electricity is actually needed. And so in order for electricity to get transmitted, it has to go through these 2 systems. So the first one, which is the next major system of the electricity grid, is the transmission system. Okay, so if you guys are driving along the freeway and you see those big metal towers that have the power lines, that is generally going to be part of the transmission system. And so these things are extremely high voltage, which allows them to be transferred at long distances with lower sort of efficiency losses. Okay, so we're talking about hundreds of thousands of volts. So essentially this very, I guess, high pressure system. Okay, and these transformers here are what are used to go essentially from sort of lower voltages up to high voltages to go across your transmission system and then to step back down to lower voltages once we get to your distribution system. So the distribution system is similar to the transmission system. It is mainly functioning to transfer the electricity from one point to another. But these occur in sort of more localized areas at much lower voltages. And so when you look around, if you look at the sort of wooden poles with the power lines, that's typically what we think of when we're talking about a distribution system. So these big long distance transmission systems, they go through these substations to go down in voltage, and then to these distribution substations to go down in voltage. These can service sort of fairly large areas. So if we're thinking about Davis, for example, does anyone know where the distribution substation is in Davis? Yeah, off. It's like at 3rd and L. Yeah. That like PG&E sort of big lot area. That's where this happens, your distribution substation. And from there, power will then get sort of distributed across the sort of local distribution network. And so Davis only has one substation. In larger cities, you might have several. And typically, you're going to see them distributed like this. There are some systems which have a lot of this equipment underground, and that can have a lot of benefits compared to having these sort of outside, right? You don't have to deal with things like heavy wind conditions, things like trees falling onto your power lines. Okay, but it's also a lot more expensive, right? To think about digging up all this trenching and then laying down the equipment, and the equipment itself has to be a lot more robust, so you don't have to dig it up to perform maintenance. Yeah, so underground is a thing, but you're not going to find that everywhere. And eventually, this power will make its way to the end users via the distribution system. Okay, and so obviously, this is kind of a fairly big simplification of a lot of details about the sort of power system. We're not going to talk about power flow and optimization and that sort of thing. There are entire classes that you could take just about the power grid. Okay, so we're going to focus in mainly on generation today and thinking about how electricity is produced. So if you'll recall in some of the earlier lectures, we showed this example of if you have a generator, right? I can get something to spin to produce electricity. And that's like the entire name of the game here. If I can spin something, I can make electricity. Sort of a large scale version of that is using a turbine. Okay, that's essentially a type of generator. Okay, and I'm going to basically be putting energy into a system in order to cause the turbine to spin, which will produce electricity. So nearly all the electricity in the world is produced this way. Okay, the vast majority. So whether we're talking about coal or natural gas, nuclear, wind, hydro, all of those fuel sources produce electricity in this way. Our one exception is solar, which we'll look at in a bit, right? But solar has no sort of moving parts. Yeah.
What is meant by hydro here? Because I know like most electricity things, they heat water up and then it spins propellers. So what do you mean by hydro?
Yeah, hydro. So if you think of a dam that creates, and we'll look at an example of this, but essentially if you dam like a river, right, you create a potential pressure from having water at a sort of elevation, and then at the bottom, you can capture that potential energy. And the way that it's captured is actually through a water turbine. So think of like essentially a fan underwater that gets spun via the pressure of the water getting pushed through it. Yeah, and so a little bit different, right? Because this is getting spun by water pressure. This is getting spun by wind pressure, and the nuclear, natural gas, and coal are getting spun by steam. But at the end of the day, they're all basically different versions of turbines that produce electricity. Okay. So first one, steam turbines. So coal is combusted to heat water. So essentially this diagram here shows the sort of inner workings of a coal plant. And the way this works is you get coal, it goes through a mill, gets ground up into this sort of really fine powder, right? You can imagine that if I have like a brick of coal and I tried lighting it on fire, that would be really different than if I sort of ground it up into like a fine powder and lit that on fire, right? You have a lot more surface area to work with, it's more combustible. So this goes into a furnace here that you can see in sort of phase 3. And the combustion process is happening within this furnace, and you can see that it's heating up some water in these pipes here. Okay, so that water gets so hot, turns into steam, and essentially gets pushed through your turbines here. This causes your turbine to spin and generates electricity through your generator. One of the things that you'll note is that this loop here of the hot water going through the turbine is actually a closed loop. So essentially, you can think about the idea that if I wanted to pass steam through my turbine, I would want it to be sort of fairly high purity. Okay, if you have weird stuff in your water, it's probably going to start to damage and degrade your turbines pretty quickly. And so this is sort of a really pure water stream. And the way that you can avoid having to kind of keep cleaning the water is you have it in a closed loop. And then you have a separate loop here that contains cool water. And through the condenser, it's going to take the hot water out of the turbines, condense it, the steam out of the turbine, condense it back into water, and the cool water gets heated up and then evaporates. And so this water source, which is in a separate loop, that can just be stuff coming from like a river. Okay, and so these things consume quite a lot of water, but the actual water that's going through the turbines is sort of being recycled. You'll note that there are two stacks here. There is this thing known as a cooling tower, and then you've got your chimney stack. Okay, so in the cooling tower, this is only water being evaporated. And so these things are typically going to be a lot lower to the ground. Chimney stacks can be hundreds of meters high, and the whole point of this is all the combustion byproducts of exploding your coal will essentially get filtered through this chimney stack, which may have some technologies to help clean the combustion byproducts to the best extent possible. Okay, and so these guys, it's just water coming out of, not very dangerous. It could be pretty hot, so I wouldn't recommend sticking your head in there. But the chimney stacks, you definitely want to avoid kind of breathing. Yeah. Yeah, yeah, exactly. And that way you don't really have to worry about sort of purifying all this water. They grab that just from sort of local streams and rivers. So this is a thermodynamic cycle. It's known, for steam turbines, this is known as a Rankine cycle. And it's about 35% efficient in practice. And so when I mean efficient, right, this means that this coal here has some kind of energy content, okay? And then the electricity coming out of your generator has some energy content. And you are able to get essentially 35% or so of the coal energy out into electricity, and the rest of it is getting lost as heat. Any questions about this? So I should mention nuclear reactors also have a similar type of process. And we're going to look specifically at a nuclear plant in just a moment. But it's also using essentially the same thing as a steam turbine and going through essentially this kind of process in order to generate electricity. So natural gas plants are a little bit different. These use what are known as gas turbines as opposed to steam turbines. And so this is an example of a gas turbine. And essentially you have air coming through here through a compressor. And that is going to pressurize the air, where natural gas is going to get injected here to combust with the oxygen in the air. And that causes this whole sort of mechanism to spin, right, by forcing the air out this way. And by spinning it, right, you produce electricity via your generator. So this operates through a different type of thermodynamic cycle known as a Brayton cycle. And this in itself is actually slightly more efficient than the Rankine cycle. So you can extract about 40% on average of the energy contained in the natural gas through this process. But one of the nice things about this is that you can do something known as combined cycle. Okay, so combined cycle is where I take both my Rankine and Brayton cycles and I combine them together. So one of the things you'll note is that the exhaust gas out of this turbine is extremely hot, okay? That heat you can then use to heat up water and then power a steam turbine. And so instead of waste heat, you can now capture that to produce electricity and therefore boost your efficiency. Okay, and so in a combined cycle plant, you can get upwards of 60% efficiency of the energy coming from your natural gas. And so it looks something like this. You have your gas turbine going like this, and then you have this closed cycle loop that is heating up water, passing it through your steam turbine, and then same system where you have a condenser, and then this loop gets recycled as before, but instead of coal heating it, it's the exhaust gas from the turbine. These things, if you notice, they look a lot like jet turbines. So if you think about the turbines that airplanes use to operate, those are basically the same thing. You could actually very easily just pull off a turbine off of an airplane, stick it in a power plant, and produce electricity. And that would work just fine. Yeah.
So are these combined cycle turbines that you're talking about? Is that like a common thing? Or?
Yeah, very common, because the efficiency is so high that like economics of doing this make a lot more sense than trying to run like coal plants. There are other sort of physical reasons why you do sort of one versus the other, but generally these have become much more popular over the last couple decades. They're a lot faster to build, and the economics tend to be a lot more favorable. There are other things as well. So when we think about using electricity, if I like turn on the lights all of a sudden or plug in my car, there's a sudden demand for that energy. And the way that the system generally works is essentially you have to make the electricity at the same time that it's being used. So there's actually there's this cool yeah, I should have should have thought of this actually. There's a cool YouTube video about this in the UK. There is this show that like everyone watches. I don't actually know, and basically it might be. I don't remember. It's this old video, and basically they're interviewing this power plant operator, and at the end of the show, like 40% of the population of the United Kingdom like go and put tea on. And so everyone's using these electric kettles, and all of a sudden there's this like massive jump in power demand. And so the operators have to be ready for this, and they're starting to turn on a bunch of power plants in order to meet this like crazy demand that happens like once a week from people turning their tea on at like exactly the same time. So one of the nice things about gas turbines is their ability to quickly respond to electricity demand. I can start spinning it up, pressurizing the air, injecting the gas, and combusting it. And I can within a couple minutes, I can basically turn it on to full capacity. In a combined cycle or in a steam turbine, you can imagine that I start combusting it. It takes some time to heat up the water. Okay, and so the amount of time to get this sort of up to full capacity can be upwards of an hour, 2 hours. For nuclear plants, it could be, you know, even a day or so. Yeah.
Yeah, the other thing is that the sizes vary a lot. Steam turbines are usually many megawatts.
Yep, exactly.
Whereas you have a gas turbine, it's like a high kilowatt range.
Yeah, so coal plants are going to range usually on the order of many hundreds of megawatts for even smaller size ones, up to the sort of largest ones. There's one in Pennsylvania that I think is over 2 gigawatts in size. Whereas the vast majority of these gas turbines are on the order of dozens to low hundreds of megawatts. Yeah, so size also plays a pretty big role here as well. So yeah, there are these like physical characteristics about these plants that lead to specific nuances of their operation. And again, we're not going to get too much into those details, but just know, you know, beyond some of the stuff that I'm showing you, there are sort of more details about how these work within the sort of electricity system. Okay, so thinking about the fuels themselves, very different, right? So natural gas is in a gaseous form. It can include other sort of impurities that can be sort of problematic when you combust them, but sort of compared to coal, sort of very different. Okay, when we think about, so this is kind of like a example molecule of what you might see in sort of a molecular structure for coal, right? But this doesn't represent, like, not all coal is going to look exactly like this. And one of the things that you'll see in here is that you'll have lots of impurities, right? You have things like nitrogen and sulfur in here, and that has implications for when you burn it. We're going to talk about next week air pollution, and those things are going to contribute a lot to the formation of things like sulfur oxides, nitrogen oxides, which are pretty bad for your air quality. Yeah, and so in the combustion process, right? So generically, we know that when we combust hydrocarbons, right, in chemistry, it looks something like this. You have your C and your H's combined with some amount of oxygen, and when you combust this, it produces heat, and the byproducts are going to be carbon dioxide and water. However, when you start to inject impurities, right, because it's very rare that you're going to get this sort of pure hydrocarbon, even as you, and actually, even if you do have pure hydrocarbons, if the combustion is happening at sort of non-ideal temperatures and that sort of thing, you can still get weird formation of things like carbon monoxide, incomplete combustion, so you might still be releasing methane. Anyways, the impurities within these fossil fuels can lead to additional pollutants, okay? And so in natural gas, we get things like nitrogen oxides, nitrous oxide, VOCs, which are volatile organic compounds. Sometimes you can get SO2, sulfur dioxide, which is going to be a lot more common in coal, and then some particulate matter. And coal combustion, in addition to sort of all of these things, also has a bunch of solids, fly ash, boiler slag, and a bunch of other compounds. So it's pretty bad stuff. Additionally, the amount of carbon that gets released from natural gas and from coal is about a factor of 2 different. So if I were to produce a single megawatt hour of electricity, the general rule of thumb is that my natural gas is going to release about 500 pounds of CO2, whereas coal is going to release about 1,000 pounds of CO2. All right, any questions about fossil fuel combustion? Great. So slightly different in some ways, but also very similar in others. Nuclear plants. Okay, so everything kind of on the right-hand side here is going to be exactly the same, except here you have something that's happening that's slightly different. So you have a nuclear reactor, okay, and so there is something happening within the reactor. We'll talk about what this is in just a second. And so there you have nuclear reactions that are essentially heating up water within this closed loop. And you'll actually notice that in this case, we have 2 closed loops. You have one loop of water going through the turbine and a separate loop of water going through the reactor. Why do we do this? Any ideas? You probably don't want to be dealing with radioactive water going through your turbine, okay? And so all of this purple stuff here, this is going to be water that's getting heated up by the nuclear reactions. And so you're going to have extremely sort of radioactive water being used within here. which you definitely want to keep separate from your turbine. Because imagine, right, you want to do maintenance on your turbine, and now you have to deal with a highly radioactive turbine as well. So kept separate, which allows you to do things like operations maintenance within this system without having to worry about issues related to radioactivity. Okay. And the process through which this happens is nuclear fission. Okay, so there's two types of nuclear reactions. There's fusion and fission. Fusion is the combination of atoms together to produce energy, whereas fission is breaking apart an atom to produce energy. And that looks something like this. You have a specific type of uranium, and when you add a neutron to it, it essentially splits it into these two atoms, and it also importantly gives you more neutrons. Okay, and so these neutrons can create a chain reaction, right, to react with additional uranium to propagate this reaction to produce energy. And the energy density of this guy, of this reaction, is like worlds different from anything that we've talked about, right? So a single kilogram of uranium-235 can produce 24 gigawatt hours of energy. That is like 1,000 times higher in energy density than any like fossil fuel. Or million, not 1,000. Yeah, millions of times more energy dense. All right, any questions about nuclear stuff? Yeah.
I don't know if you've heard about it. This is fission reaction.
Yes.
Right? So have you heard anything about reactions and what they're trying to do to replicate that?
Yeah, so fusion, they are sort of bombarding like hydrogen atoms together in order to produce larger atoms, and it will produce energy in kind of a similar way. It's very unstable, so it's difficult to do in like a commercial application, which makes it really difficult. The joke is that nuclear fusion is always, what, 10 years away? It was 10 years away 10 years ago. It was 10 years away 20 years ago. It's still 10 years away today. But so it's something that they can do in sort of a laboratory scale, but being able to sort of sustain it and being able to run it, right, in a setting that would produce a stable amount of electricity and also in such a way that can be controlled, I think is still a whiles off. And the other thing that I'll say about that is that the success of these power generation systems isn't just its like technological viability, it's also the economic viability. So you can imagine this idea that like we talk about fusion because it's like this that it's this sustainable energy method that, okay, you could in theory produce not an infinite amount of energy, right, but effectively like more than you would ever need, right? But also if it costs 1,000 times more than any other thing that we might have, then it's not going to be that useful. Because how many of you guys want to pay a $2,000 energy bill instead of a $100 energy bill every month, right? So the economic aspect of that is also really important to consider. I'm not an oracle. All right, what I'll say is if I had to bet, I would say, sure, in my lifetime, we will see the construction of a fusion reactor. Yeah, I think I'd be comfortable with saying that. I don't think that it will totally replace all the other sort of energy sources. I think it might be kind of like a pretty niche thing. But yeah, check in with me in 50 years if I'm still alive, and we'll see. Wind turbines look something like this, pretty simple. You got this entire thing is actually, right, the turbine. You got your gearbox in here with your generator, and then it produces power as wind causes the blades of the turbine to spin. Theoretical efficiency, so through this thing called Betz's law, it's about 60%, but on average, you are getting efficiencies of like 35 to 45%. And that means the amount of like energy being captured from the kinetic energy of wind, right? So this contains some amount of energy and you're extracting about 35 to 45% of it. Wind speeds are typically higher at higher elevations, which is why you oftentimes see, these things being located pretty high above the ground. So, these blades and a lot of the wind turbines can be the length of an entire football field. And even some of the bigger ones can be several football fields long. This is what I was referring to with hydro turbines. So they exploit the potential energy of water stored at sort of high elevations down to low elevations. So you can imagine, right, the sort of weight of all this water sort of pushing down, which you are essentially getting, you can get this as a calculation of the potential energy. And so this pressure can spin turbines in these hydro facilities. And there's a variety of different sort of designs that depend on how fast the water is flowing through, the height within the dam, and yeah, and so I guess those two are the two main factors related to the design of these. Okay, last one, which looks very different. So this is how you produce electricity from solar photovoltaic panels. So unlike everything that we've just looked at, which causes something to spin, right, to produce electricity, and actually, if you'll recall, spinning a generator produces things in these phases. So all of the turbines are essentially helping us produce three-phase power in our system, whereas this in alternating current, whereas solar power is generating electricity as direct current. And essentially, you have photons from sunlight hitting the surface of your photovoltaic cell, which has the ability to sort of excite, it'll excite some of the negative ions here, which can cause them to move through the circuit and essentially wanting to go to your sort of positive electrode, and that creates electricity through your circuit. Okay, and so this material is sort of fundamentally different in the way that it produces electricity. These guys are typically on the order of about 15% efficient. And again, that's referring to That's referring to the amount of energy that's contained in the sunlight that it's actually capturing. Yeah. Yeah, it is slowly getting better. There is kind of a theoretical maximum. I think it's around like 25 to 30%. And you're not typically going to see that too often. What I will say though is that with solar and with wind, there is an additional factor that people often talk about known as the capacity factor. And that's basically referring to how often these guys are actually on, which is different from the efficiency. Okay, and so let's say this is a 1 megawatt wind turbine, okay, which means that if it's operating at its peak capacity, I can be producing 1 megawatt of power continuously. But because the wind doesn't always blow, let's say over the course of a year, if there's 8,760 hours and you had a 1 megawatt wind turbine, it could in theory produce 8,760 megawatt hours of energy. But suppose the wind only blew for 50% of the year, then it can only produce half of that, right? So 4,380 megawatt hours. And so the capacity factor for renewables is one of the important points of discussion in thinking about the sort of economics of these things. Is like, if you want to make your money back, you have to have a good understanding of essentially like how often these guys are going to be producing electricity. All right, to give folks a sense of what our electricity system looks like. So this is a map of all of the power plants in the US. It's a couple of years old, so some things are going to be a little bit different, but generally it looks like this. The color of the dots refers to the fuel type of the power plant, and then the size of each dot refers to its generating capacity. In other words, how much it could produce in a sort of given point in time. So you'll note that there are a lot of purple dots everywhere. That's natural gas. The other big fossil fuel one is coal, which you'll see that there is a lot more sort of blue dots in the sort of eastern half of the US compared to on the West Coast. And in fact, if you look at California, you'll see there are no coal plants in California. Yeah, coal plants are not allowed to operate within the state. Pacific Northwest here is known for their hydro resources. So you'll see a lot of green dots and big green dots as well. And then in terms of renewables, the gray points that you see in sort of the Midwest here, this big swath, that is wind turbines. There is a lot more wind potential in the Midwest, and so you often will see a lot more of that in that region. And then a decent amount of sort of larger solar facilities in the Southwest. There is, oh, the one I didn't talk about, nuclear are the orange dots. So you can see how many nuclear facilities there are sort of scattered throughout the US. And if you look in California, there's one right there. Anyone know what that is? What was that? It's close-ish. Actually, the one near Camp Pendleton, that's San Onofre. That's down here, no longer in operation. So those were retired there were 2 reactors. One was retired in 2009 and the other one was in 2011, I think. So there's one left. It's slated to be retired in 3 years. It is Diablo in San Luis Obispo, Diablo Canyon nuclear plant. Yeah. Yeah, that is a hot topic, and a controversial one. So there are pros and cons to nuclear reactors. Some of it has to do with economics. The development of new nuclear reactors is very difficult because of things like siting requirements and basically the stringency with which the US requires you to get like permits and that sort of thing can drag on a construction project for a long time, which is why you haven't seen probably that many new nuclear reactors getting constructed in the US. Actually any power plant, everything here has some kind of lifetime. None of these things last forever. A lot of the nuclear plants were built in the like 60s, 70s, 80s, and they are usually rated to last around 40 years. And so you get to the end of that and you have a decision to make about whether or not you want to retire the power plant or if you want to upgrade it, retrofit it, keep it running. And there are some economic reasons for why you might choose to do that versus might not choose to do that. But then there are also these sort of like political, social things as well. Like people are, there can be a lot of opposition to nuclear power plants, right? Due to things like safety, especially after like the incident in Fukushima. There's been kind of a larger pushback against nuclear. So without getting into that subject, which can be kind of sort of touchy from a sort of pure like numbers standpoint, I will say like nuclear power plants are substantially safer than say like a coal plant or a natural gas plant, just like purely by the numbers, which isn't to dismiss some of the safety concerns and other concerns like how do you deal with the waste and stuff like that. I will say that safety concerns are probably sort of more I don't want to say overblown, but like if you have a sort of good idea of like how they operate and sort of the actual mechanisms and safety mechanisms for these, you'd probably be less worried than the average sort of general public. But again, this is like a touchy subject, so I don't want to get too into it. And then, did you have a question? No. Okay, cool. Yeah, so nuclear is definitely kind of dying out in the US. It might see a revival in the future. Don't know. Not exactly in my wheelhouse. But yeah. Okay, let's take a quick break for 5 minutes and then we're gonna come back and play a little game. All right, we'll get back to it. So we live in Davis over here. And let's say, okay, remember I was saying that basically as soon as I turn on my TV, start my microwave, right? Some power plant has to be ramping up somewhere to meet my my demand. Okay, and so I live here, like there are all these power plants all over the state, right? Like which ones are getting turned on to basically meet my electricity needs? Okay, so we are going to find out, we're going to figure out how to do this, how this works via a little game. Okay, the dispatch game. So everyone should have a little slip of paper. So you guys all are essentially power plant operators, okay? And so you should have a couple pieces of information. You will have some amount of power, which is the capacity. So this is how much power you can produce at any given time. And there is a corresponding fuel price. So for each unit of electricity, it costs you that much money to produce that power. So in other words, let's see. Okay, so like this one, this is a coal plant, 1700 megawatt coal plant. And each megawatt that I produce, let's say for an hour, costs me $86. And you guys should have sort of your own numbers there. Okay, so the objective of the game for you guys is to make as much money as possible. Okay, and the way that you make money is by selling electricity. Does everyone have one? Does anyone need? Oh, is yours blank? Here you go. Yeah, I accidentally had a couple blank ones in there, I guess. Okay, so the way you make money is by selling electricity. So rules, you can't communicate with other people. Okay, and so you guys are the power plants and I am known as the system operator. And I choose who I'm gonna buy my electricity from. So this is actually how it works in the real world. So in California, there's something known as CAISO, the California Independent System Operator. And they essentially decide which power plants that they're gonna buy power from. So this works in what is known as this sort of auction. So what you guys are going to do is you guys have to write down on a piece of paper your bid into the market. So let's say I'm some kind of power plant and I'm going to write down, let's say $40. And so what's going to happen is I'm going to go from low to high, okay, and I'm going to start turning on the power plant. I'm going to ask you to turn on, then I'm going to ask someone else to turn on in the order of lowest from this bidding mechanism. So let's say I'll say, okay, $10. Who has bid at that? And if you say yes, then I'm turning you on sort of full capacity, and I'm going to record that here. And so I'm going to choose to turn on the power plants that provides me power at the cheapest price. And I'm going to continue turning on power plants until we reach the amount of demand that I need. Okay, and so once that happens, right, okay, I have enough power plants on to fulfill all of the load that's needed. Okay, so this is the key part here. Once all the demand is fulfilled, everybody who turns on gets paid. And the amount that you get paid is not your bid. The amount you get paid is the final bid in the system. Okay, so the last person who gets turned on, whatever that person's bid is what everyone gets paid for the power that they produce. Okay? Any confusions or questions? Yes. You got to figure that out. No helping each other. This is an anti-monopoly. Okay, you guys are on your own right now. Yes. You get one number. All you have to do is write down one number, and you can't change that number. That's your bid into the system. You can't like wait to hear what other people are bidding. Okay, you write that down, and then we'll start to turn power plants on. Yeah.
And
we bidding on dollars per megawatt hour?
Yeah, exactly. Same units. Okay. So everyone take a second. Think about what the right strategy is here. Write down one number. Is everyone ready? Anyone need more time?
Are you gonna tell us how large the city is?
Well, a bunch of people aren't here, so I'm not actually sure. But I can kind of figure out. There's what, like 25 people here, or no, sorry, 20 people here. So it depends. It also depends on what people chose. I don't actually know. You'll have to just kind of guess. I'll tell you that the range of power plants of capacities is going to be on the order of anywhere between like 50 megawatts up to like 2,000 megawatts. All right. Don't worry about your workers. You're just trying to make money for yourself. Okay. We're going to start at $1. Did anyone? Okay, we have one person. Okay, great. What's your capacity? 1,200. Great. $5. Oh, yes. Did you also bid at $1? Okay. How much power? What's your capacity? 150. Sweet. $5. Yes. 1,500. Great. $10. How much? Oh yeah. Anything below 10. 1,800. Okay. Okay. $15. How much capacity? 1,000. Oh man. $20. 200. Great. $30. How much for each of you? 1,200. Okay. 100. 900. Great. Okay, what did I say? 30. So how about 40? 300. Okay. 45. 600. How about, oh yes, 1,700. Okay, that's it. Market closes. What did I say? $50? Was that the last one? 45. $45. Okay. 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 Everyone who turned on, this is how much money you just made. Raise your hand if you turned, if your power plant was turned on and your fuel cost was more than $45. Raise your hand. 2?
Fuel cost was more than 45?
Yeah, fuel cost. So raise your hand. Let's see. 1, 2, 3, 4. Okay, all you guys just lost a boatload of money, right? Because essentially you turn the power plant on because you bid in at a price, and then you made this much money per megawatt hour, but then it cost you more money than you made. So everyone whose fuel cost is higher than $45 probably just lost like millions of dollars. Or maybe not millions, but lots of money. Okay, so you guys wanted in on the action. You bid really low, and then you got screwed over because the cost of producing was too high. So what do you guys think is the right strategy here? So you actually don't need to know anything about what other people are doing. You don't even need to know any information about the size of the market. Yes, exactly. You should always bid at your fuel price. So that's exactly right. You will never lose money because you'll never turn on unless you're guaranteed to make at least your fuel price, because that could be the final bid. But that's in the worst case scenario, right? If it so happens that your bid is the final bid, and if your bid is the final bid, then you will break even. But if your bid is not the final bid, you'll turn on and you'll make some money based off of this differential in price. Okay? Does that make sense to everyone? Cool. Okay, let me talk about one more interesting thing here. Does anyone have an oil generator? All right, who has the highest fuel cost?
55.
Yeah, 55. Anyone? 88. Anyone higher than 88? Okay. So we're okay. Who has the 88? All right. We're in a unique situation here. I'm the system operator, and I'm like, okay, I need some electricity. You're on. We're gonna go all the way down the line. We're going up our what's known as this sort of bid dispatch curve, right? And I've turned everyone else on except for you. And I'm like, well, shoot, I still need electricity. What would your bid be? No, just in this particular situation, what do you think you should bid? Yeah, so you're thinking along in the right track, right? So it's like, I need this electricity. You're the last guy. I have no choice but to turn you on. So you say, I want $10 quadrillion, please. And I'm like, well, I guess I have to do it because that's how this market works. So not only do you make bank, everybody makes bank, right? So the last power plant in the system can exercise like a crazy amount of market power. And so there's actually ceilings to how much you can bid to prevent this from happening. And in fact, there are some small power plants, like these crazy dirty like oil plants that can almost entirely survive based off of turning on for like an hour once a year and make crazy margins by having really high bids in these unique situations. Do you guys remember Texas last year, the crazy, what's it called, polar vortex thing that happened that basically froze a bunch of natural gas plants. And I don't know how many people sort of followed this, right? But electricity prices went through the roof. Like wholesale prices were at like tens of thousands of dollars per megawatt, which is, you know, 1,000 times higher than you would normally see. And that is caused by the sort of market operation of the system, right? Let's say I need a bunch of electricity, but then half of you guys just go offline. All of a sudden, this market starts to operate in really sort of weird ways. And that's one of the artifacts of this dispatch. Okay. Any confusions or questions about this? Yes.
Would you have a scheme where you turn on the clean energy first or prioritize something else?
Yeah, okay. Kind of. The reason why this system is good is that this lets you produce electricity in the cheapest way, right? Because you're always going to turn on the cheapest thing first, and you're going to turn on the most expensive thing last. And so for the end user, this is kind of the like economic system that makes the most sense. Okay, so there is this kind of interesting idea though. So let me talk about this first, and then we'll think about how we modify this to do something like the cleanest. So this is a graphical representation of this concept of this dispatch game that we just played. Okay, each of these might represent like one power plant or like an aggregate number of power plants. And this x-axis is like how much total electricity they could produce. So like if you turn this one on, it would produce that much. If you turn that one on, then both of those would produce this much. If you turn this on, then this purple one on, then this pink one, and then this gray one on, that would total produce this much electricity. Okay, and then on the y-axis is the fuel cost. A bunch of these at the bottom here are zero because it's like solar and wind and really sort of cheap resources and hydro and that sort of thing. And then this starts to go up more and more like this. And so you'll be turning on power plants like this in what we call dispatch order, basically cheapest to most expensive. So one of the ways that you could modify this system, let's say you wanted to do it based off of both how expensive it is to produce, but also how clean it is. So if you introduce something like a carbon tax, okay, that would inherently modify this because in addition to the fuel cost, it's going to be fuel cost plus carbon cost. Okay, and that would do what's known as this like resource reshuffling. It would move these dots in such a way that now it's doing the combined cheapest and cleanest. So there are definitely ways you can kind of like modify this system to do things like emphasize lower sort of carbon emissions. Yeah. Yeah, so there's a bunch of different markets. So you have like usually this type of thing is going to be on what's known as a day ahead market. So basically daily. You know, there's also like a 15-minute like real-time market, which is similar to this, but there are some nuances to the way that works. Okay, so that's kind of on the supply side. And so what does that look like here? Okay, so this is an example output dispatch. And what the heck is this going on here? Okay, these curves represent the demand profile in Southern California Edison. So that's Los Angeles, the sort of greater Los Angeles area. And each of these humps like this is the electricity demand over the period of 24 hours. Okay, so this is about 1 week, or let's see, this is like 8 days. Okay, and so this is like in the middle of the night, and then people start waking up, using more electricity and so on and so forth, turning on the AC, and then in the evenings, that electricity demand starts to fall off again, okay? And every day looks something like this. And then here you can actually see pretty clearly the weekend, where you might have lower electricity demand peaks. So that's what the overall shape of these curves are representing. All of this stuff, this color fill inside, is telling you what power plants are being used to provide electricity to meet that demand. So at any time slice, that the supply of electricity has to match the demand of electricity. And let's say in the middle of the day, I have a bunch of solar, I have some wind, I have a little bit of hydro, and then I have some natural gas here. Okay, and you can see how solar doesn't really exist during the nighttime, you know, in this sort of time region every day. And I can also see how certain resources like natural gas plants are sort of ramping up and down to meet sort of different requirements of the grid. So this is a very sort of typical type of shape that you would see to show this dispatch output. Yeah.
So one question I had about this was if the price of electricity is set on a highest bidder.
Yep.
And that's done the day before, then why does the cost of electricity go up before 9 p.m.? Is that one of those things where it's like not the day before thing, like you're saying?
Yeah. Okay. So this is an important point. So all the stuff that we're talking about with how power plants turn on and off, and how it's operating in what in this sort of system operator, that's known as the wholesale market. Okay. We as end users, we don't get to, we don't pay wholesale rates. We pay rates that that are somewhat based off of those, but combined with other things like costs of transmission and distribution. And in the wholesale, so that's why like what you and I pay doesn't like fluctuate every like 15 minutes, right? There's this like sort of set flat rate. And that time of use rate between like 4 to 9, that is a reflection generally of higher prices in the wholesale market at that time period. So what's actually happening is this. The 4 to 9 p.m. is like this part here. This sudden decrease in solar usually is corresponding to some spike in natural gas, like a very quick ramping. So if you imagine on this dispatch curve, we're going from here up to here very quickly because you're losing, because your solar stuff, all the solar just disappears. They aren't able to, I mean, solar actually doesn't get dispatched in a traditional sense. They're kind of first takers. So once those guys disappear, you shoot up this curve really quickly, and the costs in the wholesale market are relatively high during those time periods.
The other thing that came to mind was that it costs more to distribute it because there's more at once. Is that?
Yeah.
That's not really as much of a factor.
No, it is a factor. The rapid ramping also means that like certain types, yeah, because it gets more complicated than this. Like if you suddenly need a lot of power, remember what I was saying about like coal plants having to ramp up to turn on their boilers and that sort of thing. That can preclude certain generation assets from being able to meet sudden demand. And so let's just say like all of these guys ramp really slowly and then these guys ramp really quickly. Maybe in a quick ramp event, I might not be able to leverage cheaper things here because it takes too long. So there are sort of more complexities about the market related to that. And with a day ahead market, you try to avoid some of that because you can make these forecasts that, oh, the weather's going to be really hot today. I predict that a lot of people are going to be using air conditioning. So we're going to have you guys like start ramping up earlier, for example, so we don't run into those sort of issues. But there can always be unexpected things, which is why there's also like a real-time market, which helps to smooth those kind of issues out. And of course, you've got transmission, which means that I don't only need to turn on like power plants really close to me. In the sort of bulk aggregate, you can sort of ship power across larger regions as well. We generally consider there to be sort of three major, what are known as interconnections that do not really transfer power. Okay, so this is the Western interconnect in green. You have the Eastern interconnect in red. And so there are some tie lines here, but there are like very real sort of physical constraints on, that kind of keep you from transmitting electricity sort of between these regions in a large scale. And then the last one here is known as ERCOT. This is basically Texas. They have their own grid. Okay, so we've talked about, I think, most of the sort of important elements of the electricity grid. And this class is about electric vehicles. So we're going to kind of take a step back and think about the integration of a lot of these concepts to EVs. Yeah, so there are a bunch of things to think about. So when you plug in your car, right, as a sort of end user consumer, you don't really need to think about these issues. But if you sort of care about sort of the energy implications and climate change and emissions implications, these details matter a lot. Okay, and so if I'm in Los Angeles and I plug in my car, right, the sort of locational factors are really important, right? I'm next to a bunch of natural gas plants and solar, and there's some hydro and wind, right? If I charged my car over here in the Midwest, maybe I'm next to a bunch of really big coal plants. Or maybe if I'm over in like Iowa, right, I'm next to a bunch of wind resources. And so the location of where I'm using the car and charging the car can play a big role in the emissions impacts. And not only that, the timing of it can also be an important factor. So consider that I charge right here at this time of the day. If you pretend there's kind of like a bar right there that represents all the fuel mixes, you can see that like most of this is in the solar. And then you've got like some large amount of wind as well. And then some hydro. And this little brown sliver right here, that's the amount of natural gas. So this is like 60% solar and maybe like less than, I don't know, 5% natural gas, let's say. Let's say instead I decide to charge right here and look at the size of the brown here. Okay, and so even in the same location, I could be at 60% solar versus like 50% natural gas if I'm charging at a specific time of the day. And of course, this kind of dispatch thing that we're seeing here is specific to Los Angeles. And that could look really different if you're in a different area of the country. Okay. So let's think about how you can calculate the emissions related to charging. Nope, looks like I messed up my animations. That's all right. Okay, it's 3 p.m. in Davis. I go and I charge my car at a level 2 charger for 1 hour. And let's see how I can calculate this. So let's say that during this time period in Davis, that 90% of the power being produced is from solar and 10% of it is coming from natural gas. Okay, so the way that I can calculate this, so at level 2, that's going at 6 kilowatts. And if I charge for 1 hour, the amount of energy going into my car over that time period is 6 kilowatt hours. So 90% of that is coming from solar. So 6 times 0.9, right? 90% of this energy in my car is coming from solar. And so this solar has 0 pounds of CO2 per kilowatt hour. And then 10% of that 6 kilowatt hours is coming from natural gas, which we'll say in this example has an emissions rate of 1 pound of CO2 per kilowatt hour. Okay. Pretty straightforward calculation. So this is my solar emissions rate, no emissions, 0. Natural gas emissions rate, 1 pound of CO2 per kilowatt hour. Okay, and so this is about half a pound, so 0.6 pounds of CO2 emitted. And so this, the way that I calculated this is a procedure known as using the average emissions rate. And this is known as an attributional calculation. So hopefully folks can kind of see how we went about calculating this. And if you do it this way, and you're sort of in the academic world, a bunch of people, a lot of like economists and certain other people will say that you are wrong for calculating it this way. And why is that? There's an alternative means to calculate the emissions. And so let me go through how this works. Okay, same scenario. It's 3 p.m. I charge my car at level 2 for 1 hour. Okay, so on the average, we've got this guy. So 90% of the energy coming from solar, 10% from natural gas. But when you plug in the car, physically, what might happen, right, is that one particular power plant is like slightly ramping up to provide the electricity, to generate the electricity needed for my vehicle. And let's say that this solar is it's all fully on. There's nothing left. There's nothing to turn on in the solar to provide electricity to my car. And it kind of makes sense because when we think about the dispatch, right, solar is always going to turn on first, right? They're the first takers. So these guys are already on. They can't produce any more electricity for your car. So the natural gas plant is the last, what we call the marginal operating generator, right? They are the last person on the dispatch curve, and they're going to turn on slightly more to produce the electricity. And so it's the natural gas plant that's actually meeting the load for the vehicle. So now we have a different way of calculating it. Now, all of the 6 kilowatt hours, all of that energy is coming from natural gas. And so that calculation nets you 6 pounds of CO2. It's the exact same situation, but doing it this way via the what's known as the marginal emissions rate, which is a consequential type of analysis, yields 10 times as higher CO2 compared to the average emissions rate, right? And that's entirely a factor of the way I decided to do this calculation. Okay, so which one is correct? The marginal or the average? You say the average, or you say the which one? What do you guys think? So raise your hand if you think the average is correct. And raise your hand if you think the marginal is correct. Okay. Yeah, so there is not a consensus on this, and there's pretty heated disagreement about this as well. And you can make electric vehicles look better or worse depending strictly on this method of calculation. And there are good arguments kind of on both sides, right? Like for this one, you're basically saying, well, okay, like there is this thing that's happening, I plug in the car and physically I'm trying to capture the power plant that's turning on in response to charging the car. And so that kind of like makes the most sense, right? But then, you know, for the average, you're kind of like saying, well, you know, why is it that the electricity for my car has to come from the natural gas plant? Like, why not the electricity from your fridge or your TV, right? Like, how come certain ones get to be clean and certain ones get to be dirty? Okay, so there are some sort of, I don't want to call it like a philosophical debate, but like there are very sort of legitimate reasons why certain ones kind of make sense in certain situations versus the other. Yeah.
The reason why range values
Yeah, well, that's what I do in a lot of my work is I just show both of them and I'm like, all right. But oftentimes it can be like a really big difference. And like when you, let's say you're doing this analysis and you're comparing and you say like, oh, better or worse than a gas car, like one of these might be worse and one of them might be better. And if you show both of them, you're like, well, if you calculate it this way, it's better. And if you calculate it this way, it's worse, right? Like you could have situations like that happening. And you know, reviewers might get confused. The audience for a particular sort of study might not quite understand the nuance between like an average and marginal. So this is kind of one thing to watch out for when you look at like studies about how sort of clean an electric vehicle is compared to like a gas car. Yeah.
Yeah, one thing that like media and public especially don't really know very big handle on. So seeing something cited in the media, be skeptical and actually like oftentimes they won't say but like just be aware that there's a little bit of there.
Yeah, and it can. Yes, yeah, and it can make a really big difference. Like right in this example, you know, a 10-fold difference. That's a lot. That's it doesn't get more kind of extreme than that. So yeah, unfortunately, not an easy answer for stuff like this. Okay. However, you know, this also, okay, we're gonna kind of move away from some of this discussion about the emissions. You know, these are the two sort of canonical ways of doing these calculations. But thinking about sort of the interactions with the grid, now we can get a little bit more nuance when we think about topics that we've covered a little bit in the past. So specifically related to smart charging and kind of what that means in relation to the electricity grid. So what is smart charging? So let's think about it this way. Okay, let me actually jump back to here. So there's this thing where like you have a bunch of natural gas here, and then a bunch of solar here. You can imagine that if I were to shift just the time that I charge the vehicle from, you know, nighttime to daytime, maybe that makes a big difference, right? And so for a single car, the sort of concept here is that like maybe I receive some kind of signal that tells me, hey, why don't you charge a little bit earlier in the day? Maybe charge when it's all solar, right? And so if you think about these sort of demand curves that we looked at before, right? So over the period of the day in aggregate, what does the demand curve look like? If you do this kind of procedure for many cars, right, maybe I can shift this curve to charge a lot more during the daytime. And that's kind of the premise of smart charging here. And so why would we do this? It lets you charge when it's cheaper, so you might be able to save some money. It's also charging when it's cleaner, so it's better for the environments. And then you can also reduce stress on the grid infrastructure, right? You can imagine, you know, similar to that example that I was talking about in the UK, where everyone puts their tea on at the same time. Here, you can imagine an analogy where everyone goes home from work at 5 o'clock and plugs in their electric car at the same time. And, you know, if the entire population of California eventually transitions to electric vehicles, that's going to be crazy for our grid to handle. And so with smart charging, like if you can provide some kind of signal that encourages at least some people to start to shift their behavior, you might be able to get a whole bunch of different benefits, right? So example schematic of managed charging. This might be the ISO. So the system operator that I was playing the role in the dispatch game, or the utility, they might provide signals to like a building or to a charging station that can then interact with your vehicle to basically decide or provide information about whether or not it's like a good time to charge. There's a lot of technical challenges related to this. So what sort of external signals would be used? What factors should smart charging try to address? How can you do, like, would Ford have their own separate system versus GM versus Tesla, right? You have to deal with an ability to kind of standardize these procedures and the hardware to support this. Is that going to be in the car? Is it going to be in the charging infrastructure? Are you going to have hardware that people have to buy for their homes, right? So there are a bunch of these sort of technical challenges that need to be overcome. And then behavioral challenges, which in my mind are probably a lot harder than the technical challenges. How will customers be convinced to participate in these sort of smart charging schemes? And then are you going to like take control of charging out of the customer's hands? Can you imagine that? Like if you own a car and someone else comes by to refuel your vehicle and you don't have control over when you get to like go to the gas station essentially. And maybe that's good if they pay you and you make money to do that. but what if you suddenly need like a charge on your vehicle and you don't have it, right? Yeah.
Researchers just look at the demand curve and say, we want to shift it this way. Power companies just make charging substantially less cheaper.
Yeah.
Essentially more cheaper.
Yeah. Yeah. That's so people talk about that. That is definitely one of the sort of like more hands-off systems that people think about with smart charging. There are some challenges associated with doing it like that, but for sure, that is one way, just like pricing it at the right times. And then sort of more complicated vehicle to grid. So this involves any scheme where the electric vehicles can discharge electricity back into the grid. So you're basically turning your EV into a storage asset. Okay, so traditionally, right, this is how it works. Our grid provides electricity to our car, which then we use to be able to use for mobility purposes. But in this case, with V2G, I can send electricity back into the grid. So we think about that dispatch curve where it's like cheaper in some times of the day, and then it's more expensive in other times of the day. Maybe you could buy electricity when it's cheap and sell it when it's expensive, right? That's one possible scheme of doing sort of energy arbitrage. And there are some sort of protocols being developed to try and do this sort of thing. Okay, and so the last thing that I'll leave us with is sort of, I'm not entirely sure, right, where we're going to end up in the future. But what I will say is that there is a tremendous potential, and probably someone is going to capture some of that potential, right? So California plans to have 5 million EVs on the road by 2030. If you assume roughly like 50 kilowatt-hour batteries per vehicle, that's 2.5 gigawatts of instantaneous capacity. If even 1% of those vehicles were plugged into DC fast charging, at half of those, that would be 16.5 gigawatts of instantaneous capacity, which is huge. That's like half of all the electricity peak load in California at once. And the total battery capacity is currently, in 2030, would be something like 250 gigawatt hours, right? That's enough electricity for like 5 peak hours of California's electricity demand in a year. And so California currently has 1.4 gigawatts of storage capacity. So compare that to, you know, some of these numbers, and the daily electricity usage would be 700 gigawatt hours. So nearly a third of all electricity usage in a single day in California would be equal to the capacity of all those batteries. Right, so this is going to be, one way or another, this is going to be really big economic impact to our electricity system. And there's a lot of potential opportunity to capture like economic activity there. And there are companies kind of jumping at this now, but it's kind of the Wild West. So this is a very sort of interesting area of study these days. Okay, great. That's it for today. Next class, we're actually going to have a guest lecture about end of life and secondary use of batteries. So we'll look forward to that. I'll see you guys on Wednesday.